me show you a little bit with my camera what Labradorescence looks like, because that's one of my favorites. That's one of my favorites. Ah, there's a good one. So, Labradorescence, but do you see those yellows and the green and a little bit of that orange up there? And the blue? Do you see those colors? So, it looks kind of like a fish scale almost. So, it's like a kind of a normal brown or whatever, nothing crazy. You tilt it, and the color changes. Very cool, isn't it? Yes, this is Labradorite. Labradorescence literally only occurs in this mineral, Labradorite. This mineral is very special in that it's the only one that does this specifically, which is why it's given its own name, Labradorescence. And it has to do with twinning in the mineral. And twinning in minerals is where you get two different mineral crystals that grow parallel to one another. And you can get this repeated pattern. And in this case, this is actually caused by exolution of lamellae, which we'll talk about tomorrow. God, that's so cool. I love that. Opal is play of color. So opal is a mineraloid. It's actually not a mineral, and it's because it's amorphous. One of the defining factors of being a mineral is it has to be a solid. And because opal's amorphous, it's not. It's not truly a solid. And it's not a solid because of its structure. So you get these little amorphous silica spheres. Well, they're silica dioxide spheres that are hydrous and amorphous, and they're cemented together with another slightly different in chemical composition amorphous variety of silica dioxide that's hydrous. So you get two slightly different varieties of SiO2, hydrous SiO2, that's amorphous. One cements the little spheres, and the other is the little spheres. And the little spheres, when the light actually penetrates or absorbs into the mineral, some of whatever's not absorbed, whatever's reflected back, you see these, you see that diffraction of light because of those little spheres inside the mineral itself. It's really, really strange. All right, so play of color, CHAToyancy, Labradorescence, Asterism, and Fluorescence. We've talked about play of color in opals. We've talked about asterism in star sapphires and rose quartz. We've talked about Labradorescence in a different day with the mineral labradorite. We've talked about fluorescence way back in the day. So we're just going to kind of briefly cover fluorescence. And I don't think we've ever talked about CHAToyancy. So play of color is exactly what I just talked about earlier. It's specifically found in the mineraloid opal. Again, opal's actually a mineraloid because it's amorphous. It's not a solid, and that is one of the criteria for a mineral to be a mineral. It has to be solid. So, although it has a chemical formula and everything else, it's not solid, therefore it's a mineraloid. Its chemical formula is SiO2 with a specific number of water molecules, and it can vary depending on the variety of opal because there are different varieties of opal. Where the way the structure of opal works, yes, it is like tiger's eye. That's exactly what it is, Sylvan Wing. Yes, I'm so happy you know that. Solid as in not amorphous or a liquid. Yes, Ben. Not a liquid, not a gas. It has to be actually solid. So ice can be a mineral, and then minerals forming from magma. Quartz, things like that, of course, will be minerals as well. Things precipitating out of water, like evaporates, can be minerals. Halite, sodium chloride, your table salt, that's a mineral. It's a solid. Although it can form in water, once it forms, it is actually a solid, has a crystalline structure. Is everything made out of SiO2? No. That is the basic building block for the chemical group of the silicates only. So the SiO2 tetrahedra, which we'll go into next week, that is the basic building block of most of the silicates, if not, I think all of them. And I think I'm thinking of feldspathoids, but that's another topic that I need to refresh in my brain. Anyway, SiO2 is a very, very common theme in many silicates, but it's not the only mineral, no, because you've got your carbonates, your phosphates, your halides, your oxides. I don't know, a lot of different chemical groups of minerals. Okay? You tend to treat amorphous things as a solid in chemistry. I'm not really sure if every categorization puts opal as a mineraloid, but I've always seen it as labeled as such in geology books. And I know that there are differences between chemistry and geochemistry in terms of some of the terminology. I know there are very specific ways in chemistry in which compounds are named and called, and I know it's not the same in geology. I'm not exactly sure why. That is something that is beyond my expertise. Yeah, ice is a hexagonally shaped mineral. There are different phases of ice that exist that I don't know much about, but the one that we know of, that we are familiar with, that is when it's naturally occurring, because again, one of the other things about a mineral, it has to be naturally occurring to be considered a mineral. So this particular mineral, ice, is a hexagonally shaped one, and if you ever look at a snowflake in a microscope or I don't know, pictures of snowflakes or ice that you've seen, you'll always notice that it's a hexagonal shape. It's really pretty. Okay, play of color. Opal, SiO2 with water molecules. It's individually amorphous spheres of silica that are about 300 nanometers each in diameter. All right? 300 nanometers each in diameter are these tiny amorphous spheres of silica that are all regularly packed, and then they're cemented by another type of amorphous silica with a slightly different chemical composition. The structure causes diffraction effects that result in a play of color. So, one of the ways in which gemologists will cut and display opal is in the shape of what's called a cabochon. And these are the smooth, rounded gems. I don't know a lot about gemology, but I do know that this particular cut with opal displays play of color in the best possible way. CHAToyancy! These are very, very fine-grained inclusions, or symmetrically oriented inclusions, rather, that are inside a mineral. And it's going to be kind of similar to Asterism, but in this case, it's not because of the hexagonal shape of sapphire or quartz. It's because of the fine-grained discontinuities, or these inclusions that are within the mineral in such a regular pattern that it actually creates this almost silky sheen when light is present on the mineral. Things like selenite, which is a type of gypsum, and tiger's eye can both produce this. Tiger's eye you can actually see here. I believe this is actually a type of Ulexite, which is another mineral that's in a different chemical group altogether than the other two minerals I previously listed. Calcium, it's a sulfate. Tiger's eye is quartz with, I believe, ilmenite in it. I can't remember the mineral in it that makes these nice structures. And then Ulexite is I think it's a borate? I don't remember off the top of my head. Ulexite's also occasionally coined TV rock because of its ability to transmit images like fiber optic cables can. Oh, it is a borate. It is a borate. So we got a borate, a sulfate, and quartz with inclusions that all produce the same kind of CHAToyancy. Oh yeah, wood can have CHAToyancy like mahogany. Mahogany wood can have CHAToyancy as well. So Labradorescence. Are you guys good with CHAToyancy? Pretty simple. I'm going to go over these pretty quickly. Okay. I'm going to move on to Labradorescence, which is a specific type of coloration that only happens in this mineral labradorite. And it's really interesting. It almost looks like kind of a fish scale iridescence that produces greens, yellows, blues, oranges. It's very, very, very unique. And a lot of people prize labradorite for this specific type of luster. I don't even think it's luster. I think it's a type of coloring. But it's a scattering of light from parallel planar exsolution lamellae. So what happens is you get, in the solid state solution, you get the exsolution, or if you want to think about it, the replacement of a specific type of mineral into a different type of mineral in the solid state. So there is no melting involved. And this is actually what happens during diagenesis in some cases. You get the calcium and the sodium end member of the same mineral. And what happens is the sodium slowly replaces the calcium. And then you get these exsolution lamellae. And this occurs in minerals whose composition varies between two end members. And they have to be pure end members. And in the case of anorthite and albite, you do have the calcium and sodium end members that are pure. And it works very well. In fact, the solid solution series of that group of minerals is so perfect that there's a definition of a different mineral at each, I think, there's a specific percentage of calcium to sodium ratio that makes each of those minerals different. So there's labradorite, there's biotinite, anorthite, albite, and there's always, I think, one or two that I forget. But labradorite is a type of plagioclase. Plagioclase produces a lot of different minerals, and labradorite's kind of in the middle. I don't remember the ratio of calcium to sodium in this specific one, but it's because of these exsolution lamellae that you get these weird iridescence in this color. It's really cool. I love labradorite too. So labradorite, Labradorescence, this is actually a picture of some exsolution lamellae in a piece of feldspar or labradorite. So you can see that these are, it's called a perthitic texture, and this can actually be, no, this is exsolution lamellae. This isn't a perthite, because perthite would happen during a magma. And then this is actually my favorite diagram, because it shows the solid solution series in the best way that I know how. So you get albite is the sodium end member of plagioclase, and you get anorthite, which is the calcium end member of plagioclase. This miscibility gap right here means that no minerals can form there. It's not possible. And you could get some more mixing. Sanidine isn't super common, at least not in the environments in which I'm working in, but in igneous environments, yes. So you get these are all possibilities, but this is not. So labradorite is basically kind of right in the middle, and it's almost half and half. I mean, it's a bit more calcium than sodium, but then you have biotinite, andesine. Oh yeah, andesine's always, oligoclase and andesine. I always forget those two. And then this is what it produces. You can actually see the twinning in here as well. Twinning is another thing that that labradorite produces. Actually, all the feldspars do. Do you guys have questions about this? The differences in the microstructure cause light diffraction, producing a range of colors: blue, green, yellow, red, and a few other colors as well. But there's some of the yellows, maybe a bit of orange even, some blues. This isn't the best labradorite sample that I've seen. Let's look at Mindat. Mindat has some pretty good stuff. And if you aren't familiar with Mindat, mindat.org is one of the best mineralogy websites, period. It's basically a free encyclopedia for all things mineral in the geologic sense. So here's some labradorite. Oh my God, it's so gorgeous. Oh my God. It's beautiful. Moonstone is, I think, a type of orthoclase. I used to think it was a type of plagioclase, but if I remember reading something recently, I believe it's a type of, let's look. Let me find out for you. That's really nice. That's not even polished. And when you rotate these, the variations in colors change. That's a very purple looking one. Oh, moonstone. Let's look up moonstone. Not healing properties. It's a type of microcline, so it's a type of it is a type of K feldspar. So that would then be at this end member here. Because it's microcline, so it would be up here. It's a type of, and orthoclase may show similar moonstone qualities, but it's oh. Okay, Schiller. Definition of Schiller: variable optical phenomenon in gems and minerals related to sheen, varieties from milky to an almost metallic shimmer and vivid iridescent play of color. So this is, I think, describing all of these various properties. It's usually seen just below the surface of various pyroxene, feldspars, etc. Schiller effects are the result of thin microscopic inclusions within a translucent mineral, usually as solution lamellae, which refract and reflect light. Okay, but that's actually that doesn't include play of color though, because that play of color doesn't involve exsolutional lamellae. Labradorite does. Labradorescence does. The presence of the miscibility gap causing exsolution of orthoclase from the plagioclase during cooling. Gemstones cut from this material have been termed spectrolite. Well-developed Schiller due to microperthite produced moonstones. So it's a type of microperthite. Adularia. Oh, that's why Adularia is so expensive. I was looking at some samples on eRocks, and it apparently shows this milky Schiller, also termed Adularescence, sunstone, or aventurine. I didn't realize that it was sunstone. Interesting. It is a type of feldspar. It's a low-temperature potassium feldspar of variable structure. That's pretty cool. That's pretty cool. No. These aren't minerals from the moon, Bensai. This is just a term to describe a specific kind of mineral. The name moonstone, I think, is more of a layman term, maybe. It's not really, or a gemology term. It's not really a mineral term that we use in geology, but it does belong in this part of the chemical group of minerals. So, of course, the miscibility gap means nothing can form. It's immiscible. That means it doesn't mix. Okay? So, what happens is you get your microcline. Microcline produces some really crazy optical properties on the petrographic microscope, but that's also where your moonstones are going to be. Your labradorite, of course, is down here. It's a type of plagioclase. Now, although they form a nice solid solution series with alkali feldspars, they are a technically different mineral. These are all considered feldspars. They're all very similar. They're all silicates, but they all do vary in chemical formula. This is your calcium end member, your sodium end member, and your potassium end member. And although you can have minerals between the sodic and potassic end members, you can't have any between the potassic and the calcic end members. It doesn't exist. It doesn't exist. Except this tiny, tiny bit here and this tiny, tiny bit here. Are there different minerals on the moon? Actually, it's mostly anorthite. Not anorthite. It's a type of basalt with a lot of anorthite in it. Basalt is very magnesium and iron heavy, but there's still a lot of silicon in there. But it's not very different from the rocks in terms of its chemical composition that we see on Earth. No. Exactly. It said it too. Rock-wise, no, it's very similar to Earth chemically. All right, Asterism. We actually already went over this today. But, it's fun, and I actually think this one is really, really interesting. So you get small occlusions that align themselves inside a mineral with a specific structure. So like sapphire or rose quartz, you get a hexagonal structure. The inclusions in those minerals align themselves with this hexagonal structure, and then with the light, refracts and reflects inside. Some of it's absorbed and whatnot, and you see these star patterns. So, asterism, we have small inclusions that align themselves with the structure of the mineral in which they're included. So, sapphires and rose quartz, right? We've been talking about these. They're both what shape? What shape are they? I've said it multiple times. Sapphire and quartz make a what shape? Blank shape. Hexagonal. Yes, you got it. Yes. So, we've got a hexagonal shape, and these inclusions preferentially align themselves. Rutile, specifically in sapphire, dumortierite in rose quartz. That's the other mineral. I want to look that one up because I've actually not heard of that one. So both corundum and quartz, of course, have a hexagonal structure. So you're going to see basically little inclusions apart about at 60 degrees from one another. And you're going to see 6 little star-like patterns. Light is reflected from these inclusions and produce a star pattern, right? So star rubies, star sapphires, rose quartz. I'm not sure what the rose quartz variety is called when it shows asterism. But again, it is from the mineral dumortierite, which I actually don't know much about. So let's look that mineral up because I do want to know more about it. So this is what asterism looks like. So this is a type of star sapphire. This is a type of rose quartz. So two different minerals actually create these star patterns. This is rutile in sapphire and dumortierite in star sapphire. So you can see the way in which the inclusions actually align themselves. So you can imagine then if this mineral wasn't polished into a cabochon, that it would be a hexagonal shape, right? And you can see that these are all about 60 degrees from one another, which, and of course then this is 120 from each other, which is normal for a hexagonal mineral, right? Makes sense, right? Minerals are geometric, they're solid, they have a defined structure, defined chemical formula. So it's all these tiny, tiny needles of inclusions that align themselves in a direction perpendicular to the crystal face. But they're aligned with the crystal as it cools. I think this is really amazing that this even happens. Oh, minerals absolutely are geometric and have patterns. That's one of the things about them that are so cool. It's like, how do they form these perfect shapes? It's insane. It's insane. All right, fluorescence. This is one of my favorites because I have actually a sample of willemite. Willemite is very strongly fluorescent, but it's a specific rock or mineral from New Jersey. And it's that locale that actually fluoresces in that way. I don't know if there are samples elsewhere or if they fluoresce. But basically, you have to have a source of UV to shine on these minerals. It bounces an electron. Excited electrons are raised to a higher energy level when you shine the UV on it, and they're excited, they bump up to an energy level, and then when they fall back, they emit energy in the form of visible light, and then we see these bright colors. Okay, so the moment you take away that UV, you aren't going to see those bright colors anymore. You're just going to see a normal rock again, assuming you have actual plain light, right? You have some light turned on. Now, oftentimes you'll have to turn off a lot of your lights to be able to get that nice fluorescence. And buying a black light from like Walmart isn't going to do the trick. Usually those are just bulbs painted purple. But if you do get a proper UV, make sure to read any warnings because they can actually cause sunburns. It's not safe to shine UV on your skin, especially not for long periods of time. So just make sure you read anything that you need to, because usually if you buy a proper UV, they will have instructions with warnings as well for what you need to do. But that's fluorescence in a nutshell. Phosphorescence is very similar, but when you take the UV away, it'll still remain phosphorescent for a short time. So things that glow in the dark, like glow-in-the-dark stars, are something that would include some phosphorescent type of chemical or mineral. So that is the end of this portion of minerals and color.